So now in this video I thought we would take a quick look at the circuit that I just put together. I didn't build a schematic or anything. We have 5 volts at the power supply right there. And what's important about this circuit is that we are lighting 4 series red LEDs. So you need at least 6 volts to get a slight trickle and a very slight glow. And these are actually fairly bright. They're actually okay. I could use those in a circuit that bright. The problem is though, we got about 4 or 5 milliamps of current going through them, and as you can see, the power supply is providing about 40 milliamps of current. So now that's not as bad as it sounds. If we were able to get 10 volts across here and 20 milliamps of current flowing through it, that would be the same power that we're powering it. So it would be twice the voltage, half the current is the same power. But we're not even getting 10 volts across here, and we only got about 4 or 5 milliamps of current going through them. So not terribly efficient. So I'm not going to go through all the effort to make a schematic and everything because it's not a great circuit, but it does what it needs to. So now the magic that comes with the higher voltage in this particular circuit is the inductor. So you can see we got a path here. When we first apply power, we can get about 4.5 volts to this capacitor pretty much instantly. And but again, that's not enough voltage to power the load. So we have the transistor here. That's a diode drop that lets a higher voltage move its way to charge the capacitor, but then when there's a lower voltage over here, current won't come back. It has to go through the load or just keep the capacitor charged. In fact, we can yank this capacitor in this circuit. I see no difference, but I think it's still a good idea to add it. That's 100 microfarad, by the way. Value doesn't really matter though. So in any case, we apply power, and when the 555 timer has a high output, that turns on this transistor. It's a 2N2222, which is actually wired as a current source, but it's being switched on and off by the 555 timer. So it's a current source because we have these 3 resistors to the emitter, the bottom pin right there of the 2N2222. It's a NPN, bipolar junction transistor, by the way. And you can see they all come to the negative supply there. So each one of these is 100 ohms. That's the equivalent of 33 ohms because they are in parallel, but they're sharing the current so that they hopefully don't overheat. Now, I didn't mention it earlier, but this is a 0.33 microhenry inductor. So, you know, not a terribly high amount of inductance, but I see it a lot in schematics. So I should be able to make a good circuit with this. But in any case, takes a little bit of time for the current to start conducting, which is, you know, somewhat high in this circuit. And also it takes a little bit of time for it to stop conducting. So when the transistor turns off, then current doesn't conduct that way anymore, but it still has to go through the inductor. So it pumps more current into the capacitor, raising the voltage, and also we got the load here that can draw current right there. So as long as the voltage is high enough, current also goes through there. This diode lets, when we have a higher voltage over here, current flows that way, but current cannot flow that way when the voltage is lower over here and higher over there. It just stores the charge, or the load uses it. So that's the basic principle of this circuit. This other diode here is just for safety. So this is a 22 volt Zener diode. So the cathode is over there, anode is to ground, and if we get to 22 volts at this point, then current will start flowing through the Zener diode, preventing the voltage from rising higher. So since this can't provide enough current to raise the voltage that high, not even close, we don't need this in this circuit. But if we remove the LED or something, then the capacitor can charge above 22 volts, but this will limit that. So I believe you can charge these up to 50. So it is just keeping the capacitor from overcharging and popping, you know, getting fried. Over here we have a 555 timer. So it's an NE 555 timer wired in astable mode, which means the output just keeps going high and low. And it should be about equal timing because we have a 100 ohm resistor there and then a diode to charge the capacitor. This capacitor is 10 nanofarad or 0.01 microfarad. Means same thing. I grabbed it out of this Joe Knows Electronic Semiconductor kit right there. It's just the value I found that works the best so far. I haven't found better, although I'm sure I could if I really tried. So that's the charging process, and then it discharges through the same value of resistance. So the charge time and the discharge time, going to pin 7 there, is about the same. I'm not going to go through all this. It's astable, but in any case, astable 555 timer. So that sets the timing, you know, pretty quick. I don't know exactly how quick. And also, if we had an integrated circuit that could respond faster, could switch, go to a higher frequency, this circuit might work better. Now, I have a 1000 ohm resistor here that is delivering current from the output to the base. It's given the high-low signals. Either it's like 3.5 volts because it doesn't get to 5 volts coming out, or 0 volts, ground right there. Jumps between those two voltages. And so we need a fair amount of current to the base to emitter, which is wired as a current source. So again, if that doesn't make sense, look up NPN bipolar junction transistor current source circuits. But in any case, we need a somewhat low value resistor here because we need, you know, a relatively high amount of current base to emitter there so that we can get a whole lot more current going collector to emitter. And of course we should get numbers with this. So we got the multimeter here set to measure voltage. Don't have to do anything but turn it to V. There is the power supply. We will turn it on again, and we have our load here. So we're not going to measure the current directly, but we can measure voltages and calculate the current. So there you can see power supply, about 5 volts right there. But across the load we have, it looks like about 8.8 volts, and for the LEDs that's about 7.69 volts across them, so higher than the power source. Now if this was a 1 kilo ohm resistor, we would have 1 milliamp per volt, but this is about 1/4 of the resistance. It's a little less. It's a 220 ohm resistor, so a little less than 250. 250 ohms would give us 4 milliamps per volt. So there you can see, you multiply that by 4, and we got about 5 milliamps. Hopefully that makes sense, that we have going through the LED. So they're glowing, you know, significantly. We could get them brighter if we had a higher voltage going across here. But this is about all the current we can provide with this setup the way it is right now. I could probably make it better, but I'm done fiddling with this. And again, it's not good enough for me to draw a schematic. I wouldn't want people building voltage boosters like this when you can buy a voltage booster module for about $1 that can provide tons more power and a lot more efficiency. So in any case, hope you still enjoyed. Make sure you turn the power off when you're done. And thanks for watching. Check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.